So, this is the concluding lecture of the course on convex optimization. The course on convex optimization is really not complete an undergraduate course in the true sense of the term. It has a mix of graduate and undergraduate flavor, both having a bit of algorithmic flavor in some sense for a very particular class of problems, and also having a good amount of theoretical flavor. Now, today's lecture, usually in the last concluding lecture people summarize what they have done in this course and how could you use this course for your other activities. So, but I thought that I would be giving you some sort of an entertainment lecture by telling you some interesting snippets about convex optimization and telling you some details about things. So, I will let me just say today's lecture is an entertainment lecture. So, you relax, forget your notebooks, just listen to what I am saying. We will really look into two aspects, KKT conditions, and we will revisit them. And number 2, the use of strong convexity Now, this revisiting of KKT conditions we will do first and will take the least time. This was due to a work of John B. Lazare, which was published in the journal called Optimization Letters in January issue of 2010. This goes under the title called representations of the feasible region in convex optimization. See, in general what is the meaning of a convex optimization problem? So, we come back, make a full circle and come back and ask the question, what is a convex optimization problem? This problem simply means you want to minimize a convex function x f over, or more succinctly like this, where f is a convex function and C is a convex set. Now, in general we have always assumed in this course that this set C in most cases is described by the set of all x's for which gix is less than or equal to 0 for every I from 1 to m, and each of these gi's are convex functions. If C is described in such a way, then this convex optimization problem is usually called a convex programming problem. That is why the CP sign is used in most cases. This is called convex programming. But usually it means minimization of a convex function over a convex set. Now, the question is to represent a convex function set in terms of inequality constraints. Does it mean that I always have to consider functions, each of these functions to be convex? That need not be the case, because if you take the set C, C naught 2, such that so if this is my feasible region, then this feasible region depicts the following convex set. Now, if I consider this function g1x, this is not a convex function, but though. So, there are other functions which are convex, but this is not a convex function. So, I can write this as minus x1 less than 0 minus x2 less than 0, which would be convex function, but g1x is not a convex function, but the set C ultimately is convex. So, here what is happening is a representation, in the representation of the set C, I am forced to take in a non-convex function, at least one of the functions is non-convex. So, it is really not a convex programming problem in the sense of terminology, but it is a convex optimization problem. So, what we do is the following, that the question we ask is for the following. In this case, is KKT conditions necessary and sufficient. So, if that is the question, what constant qualifications are needed for this to take place? Is Slater condition enough? The answer is no, the Slater condition is not enough. So, apart from the Slater condition, so we will need two conditions for this to happen. And number 2, following, we will assume that all these constants are differentiable, the GIs are differentiable. For all x in C with so for every point in the boundary, this vector is non-zero, that is the idea. You see, now we are considering the condition case where C is given in terms of inequality constraints, that is C is written in terms of and this all of them need not be convex. So, sometimes we, if I just list down the constants, if there is a non-convex constant, we consider it as a non-convex programming problem or non-convex optimization problem without realizing there is a hidden convexity, because the ultimate feasible set C, that is a convex set. So, for such problems, if these two conditions are satisfied, then Lazaire proved that KKT conditions. So, this condition is called a non-degeneracy condition. Oh, GI. The KKT conditions are both necessary in this situation. So, even if all the elements of the set the represent functions representing the set C is not convex, still we can write down, we can show that the KKT conditions under these two assumptions, this is called a non-degeneracy condition. We will not go into too much detail because it is just snippets. The non-degeneracy condition. So, Lazaire proved that KKT conditions are both necessary and sufficient. So, this is one interesting aspect, that even if your representation is not given all biconvex functions, you can still have a necessary KKT conditions to be necessary and sufficient, provided that not only Slater condition holds, but something else additionally also holds. It has also been recently brought to the non-differentiable situation by a colleague of myself and me and with a colleague. So, let us forget that part and let us go into a more interesting part, which is more interesting from an algorithmic point of view, and that is what we will now study: strongly convex functions in and optimization. How strongly convex functions affect optimization. So, if you have a function from Rn to Rn, a strongly convex function is one whose Hessian matrix has always got to be positive semi definite, sorry, positive, not positive semi definite, positive definite. So, for any x y, if the function is differentiable, then this is the definition of so for all x y in Rn, this is what will happen. Try it out with x square, where mu is greater than 0 is called the modulus of strong convexity. Just for simplicity, we will put mu equal to m by 2, just because we need to differentiate this part also very soon. So, once I do that, this expression would now be where m is of course some quantity bigger than 0. Now, m is nothing but twice of mu, that is nothing else. So, now this function is coercive. A thing which you have already heard before, in the sense that limit of f x is equal to plus infinity if the norm of x is going to plus infinity. Hence, there exists x star in Rn which is unique such that f of x star is equal to p star is equal to the infimum value of f over Rn. So, whenever the function is coercive, there would always exist a unique minimizer. The uniqueness comes from the function being strongly convex. Strongly convex function is a subclass of strictly convex functions. So, strongly convex functions are those subclass of strictly convex function for which the Hessian matrix at every x is always positive definite. For quadratic problems, strictly and strongly convex classes coincide. Now, we are first, so our question is the following, which makes very good sense from the point of view of computation. Of course, if you want to compute grad fx and possibly put that equal to 0 and get the answer if you want to solve it. But here if you would observe very soon that it is in order to solve this problem, we really again have to go back and apply standard algorithms. Just doing grad fx equal to 0 might not, but grad fx equal to 0 will not only give an approximate answer. So, given any x, so the natural question is given any x in C, so one of which could be your approximate answer, given any x in C, given any x in Rn, not C, can you estimate, the question is can you estimate this distance? That is the question. That is a absolutely relevant question from the algorithmic point of view, because if you are stopping, you do not know the exact x star, you are stopping at your algorithm and taking that xk as your solution, how good is your approximation? That is a very important thing from a numerical point of view, and so getting an upper bound on this is a very important issue, and that is what is the subject of error bounds, which is a very exciting area of research in convex optimization is all about. So, let us take a careful look as to how we can do it. We will be, our first step, we will claim that P star we will prove this. For the given x, this is P star is always bounded below by this number. For any x, this is always true. So, how do I do it? Now, for a fixed x, once I fix the x for any other y, let us look at the left hand side of the, right hand side of the expression for strongly convex functions. Now, of course, we have started in our definition of strongly convex function, we have started with the case where f is differentiable. If I am not getting into the issue of when f is not differentiable. So, you see a strongly convex function is always convex, because this is greater than or equal to 0. So, again this whole thing is bigger than this whole thing, but a convex function need not be strongly convex. So, example f x equal to x square is strongly convex, f x equal to x not strongly convex. F x equal to x to the power 4, x is in R, of course in this particular cases my x is in R. So, x to the power 4 is strictly convex, but not strongly convex. So, here you see the differences. Now, look at this part. This can be viewed as a function of y for a fixed x, putting the reference as x, I am viewing this part as a function of y. So, f of y for a fixed x, this is true, and this would immediately imply infimum of f y over R n is infimum of phi x y over R n. Now, this is a convex problem, but this is anyway convex in y, it is clear, but this is affine in y this part, and this is strongly convex in y. So, this is a strongly convex function in y. So, this is what you will have, and this is nothing but P star, which we have already seen. So, P star is bigger than inf of R n phi x y. So, our job now would be to find this infimum. So, what I would do is to optimize the function phi x y by taking the gradient with respect to y, right. And so, if y tilde is the mean, and there will be a mean because this function is strongly convex, there will be a mean, just in the same sense there will be a minimum of this function. Let y bar be that minimum, minimizer rather, then phi y tilde is 0. So, this would imply immediately you take the gradient. See, now the 2 goes off, it makes the calculation look more easy. So, this would simply tell me that y tilde is equal to x minus 1 by m grad f x. So, how do I do it? Now, observe that f of y bigger than, of course, this is the infimum. So, any f of y would be bigger than this, rather I would say, sorry, I make a mistake, I have already written p star. So, p star is bigger than the minimum value of this, which is f of x y tilde minus x plus m by 2 y tilde minus x whole square. If I put down the value of y tilde here, so I will have this bigger than f x plus grad f x. What is this? Y tilde is x minus, so x will get cancelled. So, you will have a minus 1 by m grad f x plus m by 2 y tilde minus x is nothing but same as, so I will have 1 by m square so this would give me f x plus here I will, from here I will have 1 by 2 m and here I will have minus 1 by m. So, this would give me p star to be greater than f x minus 1 by 2 m So, you see that is exactly what we had discussed, that what we want to do. So, this is providing a lower bound on the optimal value. So, given any x star, I can provide you a lower bound on the optimal value, but that need to be the infimum is p star, these are all lower bound, the infimum of the function is p star, lower bound on the optimal value. So, give me any x star, I can give you immediately a rough idea of the, so the beauty of strong convexity is that give me any f and give me any x, I will tell you here if I put as 2 mu it will become 4 mu basically, this is p star is greater than f x minus 1 by 4 mu into norm of f x square. You will simply see that this thing, see here I have used the fact that this inner product, this is same, is nothing but norm f x square, norm grad f x square. So, give me any x, then I can provide you a lower bound to p star, that p star will never go below this value. P star might be much above this value, but it will never go below this value. You will soon be surprised to see that this fact would be used to really figure out how far an given x is from the original x star, which we might not even know, we might not be able to figure out. So, p star, but f x star is p star, that is what we know. But p star is greater than, by very definition, f of x plus grad f x x star minus x plus m by 2 norm x minus x star whole square. Now, here I will apply the Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality says the following. So, this would imply this is the Cauchy-Schwarz by Cauchy-Schwarz inequality. This is what you get from the Cauchy-Schwarz inequality, and so here you can apply this fact and write norm x star minus x but p star is the infimum. So, f x is bigger than equal to p star, which would imply p star minus f x would be less than equal to 0. Now, from here I will get p star minus f x is less than equal to is greater than equal to minus grad f x norm x star minus x plus m by 2 norm x minus x star whole square. Now, what do you get from here? You get the following. This is what I know to be less than 0. So, that would immediately imply that m by 2 norm x minus x star square is less than equal to so, because x star is not equal to x, then the things are obvious. X star is not equal to x, this is not equal to 0, this norm. So, we can cancel out to write norm x minus x star is less than equal to 2 by m into grad f x, norm grad f x. Now, m is equal to twice of mu. So, this would be nothing but 1 by mu times norm grad f x. So, my error bound condition for this is called the error bound. Sorry, 1 by mu okay. Now, my question is the following. Can I what does this say that okay, if you give me an x, if I compute the grad f x, norm of grad f x is giving me a measure of how near x is from x star. So, suppose I have a sequence x k going to x star. Now, on this sequence, because grad f x k is a continuous function, because if n f is continuous, grad f is also continuous. Any convex function is not only differentiable, once it is differentiable, it is continuously differentiable. But x star being the solution and it is unconstrained case, it will be 0. So, which means that norm of grad f x k again by continuity of norm goes to 0, which means that for k sufficiently large, is indeed small. So, which means that if we are actually on a sequence of points which is going to the infimum, my error bound is actually telling me how close I am coming. So, this norm grad f x, if I write down this as a function phi x, measure for the nearness of a approximate solution, measure for the nearness of an approximate solution of a strongly convex function from the original one. From the original unique solution, from the original unique minimizer. Unique, of course. Now, this thing has a property. Number 1, phi of x is naturally greater than 0 for all x in Rn. It is obvious because it is known. Number 2, when phi x is equal to 0, this would imply norm grad of say phi of x bar is equal to 0. So, it will be norm grad of x, it will imply grad f of x bar equal to 0, and since f is convex, it will imply that x bar is a solution. So, it would also, if x bar is the solution, on the other hand, if x bar is a solution on the other hand, then you always have grad of this is equal to 0, and this would immediately imply that norm of grad of f of x bar is equal to 0, and that would imply that phi of x bar is equal to 0. So, what are the properties that we have actually got? So, for phi we have got the property that phi of x is greater than equal to 0 for all x in Rn, as well as you have the property that phi of x bar is equal to 0 if and only if x bar is a solution of Cp with f strongly convex, or solution of or x bar is the minimum or minimizer of f over Rn. Obviously, f is strongly convex, it is the minimizer of f over Rn. Such type of functions, at least for this, in this particular setting, if you can find a function like this which measures actually the distances from the original solution, is called a merit function or a gap function. The important question with which we will end our talk is the following: what happens if f is strongly convex, but we now minimize it over a closed convex set C? Note that now in this case, can phi be a merit function? Phi in the sense is phi x equal to grad f x, basically phi x equal to grad f x be a merit function, be a merit function. The answer is no, there is a difficulty. because if you say that phi x bar is equal to 0, this would imply that x bar is the unconstrained minima and not the minima on C. For example, if you take the function just f x equal to x square and define your phi x, in this case would be the absolute value of f dash of x or the grad f x. So, f dash of x is equal to 0 would imply the absolute value means f dash x is equal to 0, which would imply x is equal to 0, but x is the unconstrained minimizer. So, if we minimize f x equal to x square over C is equal to 1 2, then phi x equal to mod f x, then phi x is equal to absolute value of f dash x does not work. Because here the minimizer is obtained at 1, x equal to 0 is not the minimizer, because x equal to 0 is not even feasible. So, how do I define merit functions for the interesting question now would be how to define merit functions for the case when C is not equal to Rn. I would stop my talk here, because if I continue it would really go on for at least 1.5 hours more, because there is a lot of things, a lot of beautiful things come in when you try to answer this question. So, you try to create a merit function which will work, and then there are a lot of issues about that merit function which leads to another improved version of the merit function which really works in practice. So, we will not get into this. So, we will end our talk with a hope that some of you will try to figure out this particular so called simple looking question. Thank you very much.